Okay, the last kind of equation or application problem that you have to be able to do is when two things are happening, and most of the time then the question is going to be, do they collide? Okay, so you'll have, you know, one projectile going one way, another going a different way. Sometimes they're going in opposite directions. This one happens to be where one's going straight up and one is forming a parabola. So set up the two things, so whatever the two things are, set up your x and y in relation to each other, and then when you want to find out where, like, do they collide, you basically, a couple ways you could do it, but one way is to just figure out when are the x's the same, so when are the two x values of these paths, when are they the same, and then once you know what time the x's are the same, you want to see are the y's the same. So at, you know, whatever I solve for t, let's say t is 1 second. Then I want to find out where's the y value on this one at 1 second and where's the y value at this one on 1 second. Because if their y's aren't the same, then I know, like, one might be down here while this one's up here. Or I might be up here, you know, this one might be here while this one is here. So that's what I need to find out. All right, so let's set this one up. It says Derek Jeter hit a baseball with an initial velocity of 75 feet per second at an angle of 25 to the horizontal. The ball was hit at a height of 3.6 feet off the ground. So just like the last one, we're going to set it up. I put x sub dj so I know which one I'm looking at. So 75 was the initial velocity, the angle was 25, and time is t. So for the y component of that, it would be negative 16t squared plus 75 sine of 25t plus 3.6 above the ground. So this is the baseball after it's hit by the bat. So it's hit here, 3.6 above the ground. At its initial velocity and angle, it's going to come up. Gravity's going to bring it back down and hit the ground. Again, the key point I'm looking for is that point where they intersect. So in order to save his no-hitter, I would assume why a pitcher would even think to do this, even though it is illegal to do this, by the way, a quarter of a second later, the pitcher, who is 46 feet away, so he is 46 feet here, or she, I guess, could be a girl pitcher. The pitcher is 46 feet away, throws a glove into the air, so throws the glove up, which means the angle is going to be 90 degrees. So when it throws it, he's throwing it straight up in the air at 90 degrees with an initial velocity of 35.8 feet per second. An initial height of 5.9. All right, so that projectile is just going to go straight up and come straight down. So that's a linear one, so the x value is going to stay constant. You could think of it that way, or we can use our formula and talk about that in a minute. So initial velocity was 35.8. The angle is 90 degrees. It did say a quarter of a second later. So that means that's t minus 0.25. So we have to change the time as well. And then plus 46 because it's 46 to the right. So initial velocity, angle was 90, if you can read that. Quarter of a second later, and 46 to the right. The y value of the glove would be negative 16 times its t, again t minus 0.25 squared, plus initial velocity, angle of 90 times time, which again is this time, plus the initial height, 5.9. Now to simplify this one a little bit, you can realize, you know, we know the cosine of 90. Cosine of 90 degrees is the x value at 90 degrees, which is 0. So really this whole piece goes away, it's just 0. So I could simplify this by saying x sub p equals 46, which makes sense. The p value is going to stay the same. It's going to stay 46 because you're throwing it straight up. Same with this one. The sine of 90 is 1. So I really have y sub p is going to equal my negative 16 times t minus 0.25 squared. Since this piece is just 1, I would have plus 35.8 times t minus 0.25 plus 5.9. So I really could simplify that a little bit to get rid of those signs. The sine of 90 is 1. This is 0, so all of that goes away. That's a 1. So if you want to simplify it so you don't have to type all of that in, you can do that. You don't have to. You'll get the same answers, but it may make it a little bit easier for your equations. Okay, so you set up your two Parametrics. 1 is the ball that Derek Jeter has hit off the bat. 1 is the glove that's getting thrown straight up in the air and coming back down. All right, so the question is, are they going to collide? So knowing that this, the glove goes straight up and comes back down, I would figure out, first of all, at what time is the ball going to be at that same x value? So with the x value being 46, I want to know when is that height, or when is that flight, when is that at 46 feet out? So I took Derek Jeter's x value and I set it equal to 46. When is his flight, or the ball, flight of the ball, when is that at x equals 46? So I solved. I took 46 divided by 75 cosine 25, and I got at 0.6767 seconds. That's when the ball will be at 46 feet out. So now I need to know, at 46 feet, what is this height, and then where is the glove in relation to that? Where is the glove's height? So all I had to do was take 0.6767, plugged it into Derek Jeter, so I took negative 16. Again, we're looking at height, so it's the y. Negative 16 times that squared plus 75 sine 25 times that time plus 3.6. I got 17.72 feet. That's how high the flight of the ball is when x is 46. So now I just have to figure out where's the glove at that time. So remember, when you put in a time, though, the time was t minus 0.25. So it's a quarter of a second later. So I have to, when I type it in my equation, it's going to be negative 16 times 0.4267. That's what I get when I take this time, my t, and subtract 0.25. So this is t minus 0.25 squared plus 35.8 times t minus 0.25 plus 5.9. And I found out it was 18.3 feet above the ground. So now I see that in my picture, if this is where the ball is, the glove is, about a half of a foot above it, 6 inches above it. So it looks like it barely missed it. He probably should have waited a little bit more than 0.25 seconds in order for that to hit. Okay, so there's my justification to say no. At the time when the ball is at 46 feet out, those distances are different. Now, if you want to check on your calculator, realize you can put it into your y equals. So let me get this a little closer. You can go to your y equals, put in the first function, which is Derek Jeter's. I put in the second function, and I actually put it in the simplified one without the sines and cosines, but remember it's t minus 0.25 squared, and here it's t minus 0.25. So if I want to see what that looks like, I'm going to go to Window. We have to estimate about how long the ball's in the air. So I don't know, I would maybe first guess 3. Okay, so from 0 to 3, I'll do a zoom fit, zoom 0. So it'll take a second to get the window set, but I'll do a zoom 0, and I see, the glove went this way. I saw, here's the ball. I don't see the ball on this, so I might change that. And look at all this empty space down here. Everything else looks pretty good. I don't have a lot of space on the X's. I could make my X's a little bit smaller, but I'm going to go to my window and adjust them. So after you take a guess, see what it looks like. I'm going to go to my window. I'm going to leave the 3. I think that was okay. X's, I could maybe go to 190. I don't know if it really matters. I could have kept the X's the same. But the Y's, I'm going to start at 0. And it goes up to 25, so let me just go to maximum of 28, just so we can see it a little bit better. So all I did is I got rid of the negative Y's. That was the big thing, so that I have a little bit better picture. And if I hit graph, what I was going to do, though, I'm going to hit on to stop. I'm going to go over to here to make so that I can see the ball on both of them. I just arrow to the left, get over here, hit enter a couple times, and then you see this. That will kind of slow it down a little bit, and it will look like, simulate 2 objects getting thrown. And you can see they barely missed. Now, if you weren't looking, and you want to see it again, just change your window a little bit. Maybe go from 0 to 3 to 0 to 2.9. As long as you change something, hit graph again, and now watch it. There they are, very close, and then they keep going. That almost looked like they hit. So if you want to double check it, you could go second table set, go down to here and make that independent ask. Just make sure that says ask. This doesn't matter, just independent ask. Go to your table, second graph, and then you could plug points in. So let me delete these. I could say, okay, I thought that they were intersecting, I think we said at 0.6767, I believe. So I'm going to hit enter on that time. Now that says the X value of Derek Jeter, of the ball, was almost at 46. I mean, we rounded it, so it's almost. It was at 17.72 feet high, which I believe is what we got for Derek Jeter. And if I arrow over, I see that the ball, or the glove, was at 18.26, which again, if I look at what I plugged in, I got 18.3. So it's a good way to check it, to say, okay, we thought it happened at 0.6767 seconds. So as long as you're on independent ask, you go to your table, type that time in. These are rounded, so they might be off a little bit. This one says the glove was at 46 feet out. The X value is 46. There's my Y value that I found algebraically. And if I come over here, at that time, that was almost 46, which makes sense rounded. And that was the time, or the Y value at that given time. So you can double check your answers by plugging them into your table.